Hi, welcome to another Windows Defender application control video. My name is Violet, and I'm currently a Microsoft MVP. Today I'm going to show you how to perform WDAC simulation using the WDACConfig module. This is the exact process that the code integrity engine in Windows uses. This mode shows you which one of your files will be allowed or denied if a specific WDAC policy was deployed on a system and those files were running. First, I have an Allo Microsoft template policy, and I want to see how many files in the Windows directory are allowed or denied by it. So I select the policy file and the directory I want to be scanned. Remember, these parameters support graphical user interface file and folder picker, but in this demo, I'm not using them, and instead, I'm entering the paths manually. For the threads count parameter, I selected 12. That is the number of the parallel simulation jobs that the module will use during the simulation. The more cores your CPU has, the higher this number can be, and the faster the simulation finishes. On an Azure virtual machine with 96 cores, this simulation finishes in a matter of seconds. The simulation process involves getting as many details about each file as possible and then comparing them with the details in the selected WDAC policy. This process is scalable and has many use cases. For example, you can test your WDAC policy before deploying it to thousands of workstations across your enterprise. In the near future, the WDACConfig module will have a modern graphical user interface as well, which will be suitable for people that don't prefer the command line experience. Okay, the simulation has now finished, and the results have been saved in a CSV file. They are not shown on the console because they are too many, and it wouldn't be practical to view them here. Now I'm going to open the results CSV file in the Visual Studio Code and show you what they look like. It's a huge 20 megabytes file. We can align the CSV content for better visuals and inspect them. Here you can see which file is authorized by the policy and which signer or rule in the policy authorizes it. Files can be signed or unsigned. Unsigned files are usually allowed by their hashes, while signed files are allowed by their signer certificates. Windows also uses security catalogs. They are files with .cat extension. Security catalogs contain hashes of the files that are unsigned, and this hash tells the code integrity engine in Windows to treat them as signed files to authorize them. Many of the files that come by default in Windows use security catalogs for authorization. Third parties, such as driver manufacturers, also utilize security catalogs for the same purpose. If a file is authorized by a security catalog instead of the selected WDAC policy, it will be shown in the CSV file, and the full path of the security catalog that authorizes it will be mentioned there as well. Next, I'm going to perform WDAC simulation on the same OBS program that I'm using to record this video. I've already scanned the OBS files to create a WDAC policy with the WHQL file publisher level and file publisher hash fallbacks. The levels combination I selected for my scan makes sure that any signed and unsigned files will be captured and recorded in the WDAC policy. So I selected the path to the OBS WDAC policy and the OBS install directory. I'm also going to use the no catalog scanning parameter to tell the module to skip scanning the security catalogs on the system and only consider the certificates of the signed files that are attached to them. As you can see on the console, all of the applicable files are authorized by my WDAC policy. The 4 files at the end that you can see cannot have authenticode certificates attached to them because they are .bat command scripts and .bin files. It's time to open the CSV output results in VS Code and check out the detailed output. For the last simulation, I'm going to use the NVIDIA GPU drivers directory. I've already scanned that directory with WHQL file publisher level and file publisher hash fallbacks. By the way, if you don't choose a thread count for the simulation, it will use 2 parallel jobs by default. The minimum number of parallel jobs that you can configure it to use is 1, and the maximum is the number of your CPU cores. If you set the number to anything higher than your CPU cores count, it will use the max count of your CPU cores for the best and optimal performance. So the simulation has finished, and you can see the output on the screen. NVIDIA directory contains many drivers, so there are many files with the WHQL file publisher level authorization, which offers the maximum protection for the signed files. I forgot to use the CSV output parameter, so the module did not generate the CSV output. That's why I'm going to run the command again with that parameter, because I want to inspect the output in more details. I'm going to open the NVIDIA WDAC policy, and its simulation results in VS Code to show you how to cross-reference them for deep inspection. The WHQL file publisher level can only be used with .sys files and .dll files that do not import any user mode Windows libraries. I'm going to find a file that was allowed by the WHQL file publisher level and then cross-reference it with the WDAC policy to see which signer is responsible for it. If I select the file's name and then find its file attribute, I can then find out which signer that file attribute belongs to. That signer must be Microsoft's WHQL certificate because the WHQL levels only use that certificate. That means even if a file is cross-signed 3 or 4 times with multiple different certificates, only the certificate that belongs to Microsoft WHQL program is used in the WDAC policy. The signer's name is the subject common name of the Microsoft's WHQL certificate. The signer's cert root is the TBS hash of the same certificate. The cert OEM ID is the opus info of the certificate, and that should point to the same organization or company that the file belongs to, which in this case is the NVIDIA Corporation. The opus info includes more than just the organization name, but that's for another video. The signer also has an EKU, and if we follow up on that, we will see that it's the Windows Hardware Quality Labs EKU. EKU stands for Enhanced Key Usage, by the way. I'm going to cross-reference another file, and this time I'm going to choose an unsigned JavaScript file that is authorized by its hash. WDAC in Windows supports a wide range of file types. All file types can be authorized by their hashes, but not all of them can be authorized by signature, since Authenticode signatures only work on certain file types. Hash rules are among the most secure rule types, but the level of maintenance required for them is very high, and that is why they are only used as the last resort as a fallback level. The results in the CSV file contain the full path of every file that participated in the simulation, but on the console, you can only see the file names because the full paths can be so long and impractical to be displayed on the console. The simulation engine supports all levels and fallbacks that the code integrity engine uses, so no file will be left behind during the simulation. Well, that's it for this video. I hope you enjoyed it and found it useful. WDAC simulation helps me a lot personally, and I hope it will help you too. It's only one of the many features that the WDACConfig module offers. If you have any questions or feedback, please feel free to reach out on GitHub or X. Don't forget to subscribe to my YouTube channel so you won't miss all the upcoming content. I'll see you in the next video. Stay safe. Bye.